We'll proceed in curl in calculus and especially Green's theorem. Mr. Green, you are amazing. You are marvelous. So I am pretty sure that God has given some some special brain to Mr. Green. So Mr. Green, you are amazing and you are marvelous. So what Mr. Green is so what we have seen now, we have been okay, so we have been talking about the we have been talking about vector field. So vector field is algebraic vector. So vector field is a vector whose components you can say in Cartesian coordinate x component, y component, z component. But in vector field it is called first component, second component, third component, and all components are function over x, y, z. So if that is the case, then it is vector field. If it is vector field, then if I keep changing x, y, z, then all three components will change and it will generate new vector. So vector field is vector factory. If I have a vector factory, then certainly it is vector field. If I have a vector field, then what is vector field is denoted as capital F. Capital F dot distance. Capital F dot distance vector. If this capital F is force, consider this capital F being force. If capital F is force, force vector dot displacement vector is work done. But if capital F is if it is a static vector and displacement is also static vector, then only capital F dot the capital F dot R vector or displacement vector is work done. If capital F is vector field, means algebraic vector which vary with the independent component x, y, z. If I vary function, algebraic means function, Python function where the parameters are x, y, z, and output will be a vector. Okay, that is vector field. So if vector is a vector field and the displacement vector is again algebraic vector field, then it is not dot product simple. It will land up in calculus. It is not simple numeric multiplication, numeric algebra, numeric vector dot product I can do. But if it turns into algebra, then we have to go with the calculus. Calculus is nothing but algebraic multiplication area. This is what we have seen. So when algebra comes, numeric to algebra, if you shift, then whatever multiplication operator you have, it will shift to calculus integration. Numeric to algebra, numeric to algebra, then multiplication would shift to integration. That is the relationship. Okay. Division in numeric, if division sorry, if it is numeric and it becomes algebra, then division will become differential calculus. Now they are at same level. Division and numeric at same level. Differentiation and algebra at same level. Numeric and multiplication same level. Algebra and integration same level. So if I have numeric vector and displacement vector is also numeric vector, then simple dot product will give the work done. But if it turns into algebraic vector, then capital F vector dot dr vector, both are algebraic vector. I mean capital F and R vector, displacement vector, if both are algebraic, then work done is capital F dot D. D is coming into the picture to symbolize it is now calculus. So capital F dot dr vector, it is now calculus. If that is the case, then we are into arena of calculus. Calculus only knows algebra. It does not know vector. So capital F dot dr vector dot will turn up this into a a simple algebraic equation. Then you can do integration. So what Mr. Green is saying, that if you are trying to calculate, so force vector dot dr vector is work done. If force vector is simple vector field, force vector is an example of a vector field. It can be magnetic field, velocity vector, electromagnetic field, gravitational pull, whatever it is. So force vector or vector field dot dr vector, where r vector is displacement vector or line vector, then it is also called line integral. Vector field capital F vector, capital F on top of it vector sign, capital F vector dot dr vector, where r vector is line vector, both are algebraic vector, capital F vector dot dr vector, this is also called line integration. Line integration from a point A to point B, A and B are point on the line that is r vector, line that is the r vector on top, on that line point A and point B exist. This r vector can be straight line, it can be circular line, or any haphazard, any maze kind of line, whatever. Okay, from if r vector is a curve, this is better word. If r vector is a curve, then A and B exist on r vector. Integration from A to B, vector field capital F dot dr vector is called line integral A to B. If vector field capital F is force vector and r vector is displacement vector, then it is work done. Special case. Okay. Now, if I am considering f dot dr from point A to B, consider A to A. Many times I have talked about it. A to A. A to A means we are trying to calculate integration same point to same point. But it is not exactly same point to same point. In between, it can take a path and come back to A. Like integration from A to A, same point to same point, can become integration in a loop, in a closed loop. Then again it is A to A, right? If I say integration from A to A, very nice. Integration from A to A to A to A. This is also A to A only, but it is taking full path. Okay, if that is the case, then what is line integral? If line integral is 0 from A to A, it should be 0. Theoretically, A to A should be 0. But if we take a closed loop and come back to A, it should be again 0. If it is 0, it is nice. If I take a straight line, A to A, again it is 0. Nice. If I take a rectangle from A to here, here to here, here to here, come back to A. I mean, if I have a point A and coming back to A, I take any number of paths, all possible paths possible in the world, and still it is 0, then vector field capital F is called line independent. It is not dependent upon the line, it is only dependent upon the limit A to A. Since it is A to A, 0. Because if you take any path, it will be 0. So it do not depend upon the path, rather than it is depending upon the limit. If it is A to B and I know vector field capital F is path independent, then if I have point A and point B, and if I am calculating line integral, I connect through a line, I connect through a semicircle, I connect through a circle, okay, through semicircle, okay, or through a parabola, or whatever it is. Result will be same, because vector field capital F is proved to be path independent. If I have proved it, then A to B, point A to B, connecting 2 points can be anything. It will be same thing for all possible. This is what we have seen. But anyway, now if I have a closed loop, that sign is integration C. Integration and bottom we just mentioned C. It is a closed loop. If it is a closed loop and then we are trying line integral capital F dot dr vector, capital F vector dot dr vector, then it should be 0. It should be 0. But it may not be 0 if vector field capital F is not path independent. If it is 0, then it is same as df1 by dy minus df2 by dx minus df1 by dy. Please watch previous video. So there we have talked about that if capital F is path independent, capital F is path independent means the line integral what we are calculating capital F dot dr vector, this line integral will result into a potential function, and potential function small f will be fb minus fa as per the limit. Okay, but this whatever the result what we are getting, if it is path independent, then fb minus fa small f, the full result is only dependent upon vector field capital F and limit a to b, not on the r vector. This is what we have seen. If that is the case, that capital F dot dr vector a to b equal to fb minus fa small f, and it is path independent, then we have seen to be path independent, then a small f, then capital F vector field must be gradient vector of a small f. This is what we have seen, because natural way of the calculus is a to b integration gradient of vector f dot dr vector is fb minus fa, everything in small. If this is natural way to show in calculus, then the net result what we are saying is dependent upon only gradient, only right side small f is there, left side small f is there, right side b and a is there, left side b and a is there, but right side r is not there. So this form of calculus, gradient of potential function, gradient vector of potential function f dot dr vector a to b is considered as one. This integral is only dependent upon the gradient of f. If capital vector field capital F is gradient of f, capital vector field f is gradient of a small f, that is potential function, then it is path independent. This is what we have seen. So capital F equal to gradient of a small f, that is small fxy dfxy by dx I plus dfxy by dyj, means a small f dfxy by dx equal to capital F1, because capital F equal to F1 I plus F2j. So dfxy by dx small f equal to F1, dfxy by dy equal to F2. So this is what we have seen. So first one, dfxy by dx, I can differentiate again with the y. So dfxy by dx dy, dfxy by dx dy, that is differentiating along xy plane, dfxy by dx dy, it will become df1 by dy. Now dfxy by dy was f2. Now dfxy by dy dx, above is dx dy, down is dy by dy dx, but both are xy plane. So dfxy by dx dy or dfxy by dy dx, both are same. But this side it is df2 by dx. So df1 by df1 by dy equal to df2 by dx if it is path independent. Okay, so df2 by dx minus df1 by dy in capital, df2 by dx minus df1 by dy should be 0 for path independent, whereas integration in a closed loop, capital F dot dr should be 0 in path independent. If that is true, then certainly there is a relationship between the closed loop line integral and df2 by dx minus df1 by dy. What is the relationship? Mr. Green is saying the relationship is in a closed loop integration, that is a to a, in closed loop integration, capital F1 vector dot dr vector equal to, if it is a closed loop, then there is a surface. and this loop is a boundary of the surface. You can see circular surface. So if it is circular surface, then there is a boundary of the surface along which we are calculating the line integral. If I take counterclockwise movement, this is Mr. Green is saying. If I take counterclockwise movement, then if I calculate the integration of this surface, means integration of any algebraic equation along xy plane. Surface integration means along xy plane. So he is saying df2 by dx minus df1 by dy. If this will result in an algebraic equation. This equation, if I integrate with dx dy, that is dA dxy plane, and this integration is along the surface. If this integration is along the surface, then it is equivalent to the line integral of the closed loop, that is capital F dot dr vector. So capital F vector dot dr vector integration is a closed loop, is same as integration over a surface for which that closed loop is the boundary, moving counterclockwise, and then df2 by dx minus df1 by dy dx dy. Or if I go in polar coordinate, we will see it. We will see the polar coordinate. Anyway, dx dy, dx dy. So dx dy in polar coordinate it will be r d theta dr, because we are talking about dA dxy plane, not dx dy. In Cartesian coordinate it is dx dy. But how it's possible? It means df2 by dx minus df1 by dy is 0, right? Or in closed loop integral capital F dot dr vector is 0, right? Closed loop means A to A, not necessary. If it is not path independent, if it is path dependent, what is line integral? Line integral means force into displacement if they are in along the same line. If force is in same line as per the displacement, then force into displacement, or I mean vector field into displacement, is the line integral, but not necessarily. If I see force in algebraic equation, at this point force can be like this, at this point force can be like this, at this point force can be like this. Force and displacement must be in same line. So if I take a circle, then line is the tangential. Everywhere line is changing. If this is a line, tangent is a line, the force should be like this. If this is the line here, then this is tangent, the force should be like this, but not necessary. Here force can be like this, here force can be like this, here force can be like this, here force can be tangential, because it is variable on the algebraic independent variable x, y, z. If that is the case, then for every moment I have to calculate force into displacement, force into displacement, and everything we have to add as per the integration area calculation. So it comes false in calculus algebra, because it is changeable at each part. Algebra multiplication is calculus integration. So that is the scenario. Now if that is the scenario, then in a closed loop, if vector field is not path independent, then it will not be 0. In a closed loop, if I calculate integration capital F vector dot dr vector, it won't be 0. If it is not 0, then df2 by dx minus df1 by dy will also not 0. If that is the case, then df2 by dx minus df1 by dy, whatever the algebraic equation it brings in, whatever the algebraic equation it brings in, multiplied by dx dy, means integration on xy plane, and then integration along the full. Now if circle path full surface, then it is same as if I calculate the line integral in the closed loop. If it is path dependent, then it is path independent, then this is 0. If it is independent, then it will have some value. What is the value? Then what is the value? Because it will generate torque now. Torque in the sense, if I have a vector field, and if I place an item, it will start rotating the item and pushing it through. If it is path independent, then it will not generate torque kind of situation. In that way, if this is the vector field going like this, like a river is flowing, if you place an item, it will just flow through, move through. But if river is flowing and it is path vector field, force field is path dependent, means if you are moving along the y-axis, then df1 by dy is not 0, and df2 by dx is also not 0, but df2 by dx minus df1 by dy then should be 0, that is also not 0, then it is path dependent. In that case, river will make this object flow through, but river will also this object make rotate. That is curling factor. What is the curling factor? Is df2 by dx minus df1 by dy. That is the curling factor. So if I have curling factor, and curl factor, if I integrate on xy plane over a surface, then the net result is same as that surface as a boundary, right? If I calculate line integral of the vector field along the boundary, then it will be same in a closed loop, because surface has a closed loop, right? If I have this surface, then the surface is a closed, right? I start from here, goes here, goes here, goes here, it comes back. It is a closed loop, right? Every surface has a closed loop. So if I calculate integration over any surface, that is algebraic equation for the integration is df2 by dx minus df1 by dy. That is algebraic equation. Now integrating over a surface, and then that surface is this. It is same as if I calculate line integral of the boundary, that is in closed loop, that is counterclockwise if I take, then that line integration will carry the same result. df2 by dx minus df1 by dy, that is the curl factor. So curl factor integration over the area, curl factors integration over the integration over any xy plane. Integration limit is for the full surface, same as line integral of the curve boundary, that is making boundary line, that is making boundary of the surface, close integration, close line integration, capital F dot dr vector. This is what Mr. Green is saying. But this equation will gives anyone boom, 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 in a sense, this is more powerful than the most powerful in calculus. Amazing. Mr. Green, God has made you something different. This is what I can tell you. Okay. So what we will prove Green's theorem. We are not running away that we will not prove Green's theorem. We will prove Green's theorem. What is the importance of the Green theorem? Can you tell me one thing? If I have equation like minus 2yi minus 2yi, this is vector field, minus 2yi plus 2xj, this is vector field. What is the line integral of this vector field along a circle? Now you go and calculate circle's formula, that is x square plus y square equal to a square. And now line integral is minus yi plus xj d of xi plus yj. Now yj, now full it will turn into f1 dx plus f2 dy. Now f2 is x, f1 is minus y. Now x is x, y I have to substitute with a square root of a square minus x square. So minus a square root of a square minus x square dx plus x dy. Now you have to differentiate y. So square root of a square minus x square d of that. Whatever comes, then full add and calculate integration. Certainly you will not sleep in the night. I mean, if you calculate in the day, you will not get sleep in the night. If you calculate in the night, then certainly you will not sleep at all. Okay, but Mr. Green has come into the picture. Now Green is saying you want line integral along the circle, right? Then calculate the surface integral of the circular region. Simple. And then if you want that, that is df2 by dx minus df1 by dy along the xy plane. f2 is x and f1 is minus y. So df2 by dx is 1 and df1 by dy is minus 1. So 1 minus 1 minus 1 is 2. 2 integration over xy plane. But I don't know what is xy plane. It is circle, right? No problem. XY plane means XY plane, I can take in polar, that is r d theta dr, r d theta dr, or r dr d theta, that is r square by 2, that is the integration r square by 2. Now this is a circle. Consider circle has a radius a. This is what we have taken. So a square by 2, 0 to a, the limit. So a square by 2, 2 into a square by 2 will be 2, 2 into a square by 2 will be a square. Now theta integration 0 to 2 pi, 2 pi a square, 2 pi. Here if you had calculated, it would have come in trigonometric sine inverse and those kind of things. So quickly, maximum it would take 20 to 30 seconds. That's it. Here, it will not let you sleep in the night. Just think the difference. Mr. Green, you are something amazing. This is what I can tell you. Anyway, this is not my equation. This is Mr. Green's equation. Okay, we will prove Green's theorem, but let's say take an example. I have 2xy, 2xyi plus xyj, 2xyi plus xyj. This is the vector field capital F. 2xyi plus xyj. This is the vector field. Now question is it path independent? If it is path independent, then you remember we started capital F is gradient of any. I have to find any potential function small f for which gradient vector is capital F, means 2xyi plus xyj. Then this vector field is path independent. For that we started with f1 dx to get the fxy, and then that will be fxy plus cy. f1 dx will be fxy plus cy, any function over y. So that df1 by, okay, so df1 dfxy equal to df1 f1 dx integration. So fxy will be df1 dx integration plus cy. So the df1 by dx will be whatever plus cy and cy. So many, you remember, right? Means so many things we did to actually to get that if I can from capital F I can really deduce any algebraic equation or not. So this is what we are trying, where the line integral we brought into form of a generic form capital F1 dx plus capital F2 dy. You remember how we proved the path independence in 3 ways. Now here Mr. Green has come. So if you really want to prove path independent, try df2 by dx minus df1 by dy and see if it is 0. Both should be equal, right? So here f2 is xy. So it is df2 by dx. So it will come as y. And df1 by dy, it is 2xy. It will come as 2x. 2x certainly it is not equal to y. So it is not path independent. Amazing. Amazing. So quickly you can prove it is path independent or not. We will see many things in Mr. He is really green. Green means, oh, this is green. Green means very nice, right? Green. So very nice. So this is Mr. Green. Now can we prove Mr. Green's theorem? We are not running away. I am saying we are not running away. If I have a function f, small f, algebraic function small f, is it equal to, can I say f, small f at point b? I take any point, small f bracket b bracket close, curly bracket, function bracket, fb minus fa, small f, fb minus fa. Is it same as integration from a to b, derivative of f dy? fb minus fa equal to integration from a to b df by dy. Same thing, right? If it is gradient of f, I am integrating with dy, it will become f1, a to b fb minus fa. Same thing. Anyway, Mr. Green is saying that you have to calculate, if you want line integral, then you have to calculate the surface integral of df2 by dx minus df1 by dy over the xy plane. Okay, consider there is a rectangle. This is x-axis. This is somewhere. This is x-axis. Now this is this is x-axis. Okay, so this is x-axis. This is x-axis. Now above the x-axis I have a rectangle. Now this is point A, this is point B. From B, this is point C. A to B, B to C, C to D, D to A back. This is the rectangle. I am taking counterclockwise as per Mr. Green's theorem. And df2 by dx and df1 by dy should be both will be continuous in this region. It is continuous, consider. So A to B, this is the rectangle. This is the rectangle. This is the rectangle. So A to B, B to C, C to D, and D to A. This is the rectangle. Now, if I am trying to calculate path integral, then line integral along this closed loop, then I have to calculate capital F dot dr in a closed loop. So, capital F has two components, F1, F2. F1 I vector plus F2 j vector. So this is along x-axis, the line integral will be f1 dx. f1 dx because f2 dy will go away. f2, if this f2 along this, if I do f1i plus f2j dot I vector. So f2 will go away because j dot I will be 0. So f1 dx. So f1 dx is the line integral from a to b. Now leave this part, then it is C. Then f1 dx from C to D is the line integral. So line integral of this portion, horizontal portion, is f1 dx A to B, and another horizontal portion of the rectangle is f1 dx C to D. Okay, now f1 dx A to B plus f1 dx C to D, where point A has some y. If it is x-axis, remember this is x-axis. If this is x-axis, then it has some y, some height, and this portion has bigger height. So there is a difference in y portion, but there is no difference in x portion. If it is rectangle, if it is x1 and it is x2, in here also it is x1 and it is x2. x1, x2, x1, x2. But here it is y1, then here it is y2. Now you are getting right what I am trying to say. So line integration here it is a to b, that is x1, y1 to x2, y2. Okay, I mean keeping y1 as constant. Whatever the y1, I am not saying that y1 we will take into integration, but whatever is the y1. Okay, then a to b, c to d is same as a to b, right? Only difference is in y. Otherwise, then I can say f1 dx a to b minus f1 dx again a to b. It was plus c to d, but c is this side, d is this side. So if I do minus, then it will be from this side to this side. Minus means opposite. So f1 dx a to b minus f1 dx a to b, where this is for y1, this is for y2. This is for y1, this is for y2. Now we have learned that if I have any function f, then fb minus fa equal to integration from a to b derivative of f dy. So isn't it the same thing? A to b f1 dx, a to b f2 dy, f1 dx. So consider a to b f1 dx is a potential function g. There is a potential function g, that is a to b f1 dx. If that is the case, then we are trying to do g at this first integration is at point y1. Second integration, second function is at y2. That is the difference. So gy1 minus gy2, gy1 minus gy2. That is nothing but integration from yt to y1, y1 minus y2, y1 minus y2 means y integration from y2 to y1, y2 to y1, and derivative of this whatever g I am talking about, a to b f1 f1 dx, derivative of that d1. Okay, this is what we are getting. So this will be equivalent. If I take minus out, then it will be f1 to f2. Earlier it was f2 to f1. If I take minus out and then inside that f1 to f2, whatever we had by dy into dy, that is the integration. So f1 dx by dy is df1 by dy. So df1 by dy dx dy, double integration. One is from a to b and one is from y1 to y2 minus outside. Now if you take this side and this side, it will result in same thing. From y1 to y2, a to b, the way it happened, here it will be f2. So df2 by dx dy. So here it will be positive and first time it was negative. So net line integration, what we were trying to calculate line integration, right? From here, here. From here to here we did, here to here we did. So we will sum it everything. Now it will be integration y1 to y2, a to b, df2 by dx dy minus y1 to y2, a to b, or x1 to x2. I am not saying a to b, sorry. x1 to x2. So y1 to y2, x1 to x2, df2 by dx dy minus y1 to y2, x1 to x2, df1 by dy dx dy. If you go all along, then it will become integration. That is the scenario. Then it will become net integration from y1 to y2, a1 x1 to x2, df2 by dx minus df1 by dy bracket dx dy. This is what the Green's theorem, and this is over the surface because we are taking y1 to y2 and x1 to x2. So integration was from a to b, so that we divided into factor x1. So g, the algebraic function what we are talking, over which we did the actual play, that is integration from not from a to b, x1 to x2, x1 to x2 f1 dx. So if you do like this, then we can prove Green's theorem. Okay, this is my proof. I believe this is the only proof. It would be same thing would be available other places also. So nicely we did. We will do example in Green's theorem and we will see kind of the circulation density Stokes theorem. So many things is waiting for us.